So let's proceed then inserting all of these series that we've derived into the effective Schrödinger equation for P. You'll notice that every single term now has a sum on n running from 0 to infinity, so I can factor out that sum. Also, all of my terms now have a factor of r to the n minus 1. They are all on the same footing, so let me factor that out as well. So I have r to the n minus 1, and I'll open up a nice big parentheses. And now we start writing down our terms. So the first term is minus 1/2 the p double prime series, so I need to include a minus 1/2. The p double prime series has the r term, which I've factored out, and then I just have the remaining factors, which will be n times n plus 1 times p sub n plus 1. Great. Next term has a factor of minus L plus 1 times the p prime on r series. So we'll have minus L plus 1. The p prime on r series, apart from the factors of r, which are factored out, has this form. It has an n plus 1 and a p sub n plus 1. There's an n plus 1 that was there. Great. Next term. I've got alpha times the p prime series, so that will be plus alpha. And the p prime series has just npn times the r factors, so there's npn. And then finally, I have this more complicated factor, so I've got plus alpha times L plus 1 quantity minus 1, all multiplying the p on r series, which is written down right here at the top, which just has pn and then the powers of r. So that would be pn. And this whole summation then, according to our equation, has to match 0. Okay, that was a bit of math, but now we're really in the home stretch, guys. For this power series to be 0 for all values of r, it must be the case that, in fact, the coefficients on my series, all of these, must equal 0. And if these all equal 0, we are in a great position now, because you'll notice the only unknowns I have in here are pn plus 1 and pn. So I can solve, actually, for pn plus 1, which is the next term in my series, in terms of the preceding term in my series, pn. So let's do that algebra quickly. To solve for pn plus 1, we know how this is usually done, right? We're going to put both of these terms onto the other side of my equation where they become positive, and then I can factor out the prefactor on pn plus 1, and then I will use that and divide through by it, right? And I'll divide it on the bottom, and what will be on the other side of the equation that I'm dividing are these terms in terms of pn. So let's again imagine doing that. So we put those pn plus 1 terms to the right side of my equation, and I gathered those, and they'll be over here, and I gather my factors and divide through by them. So I just need to write down the sum of these two factors with plus signs, of course, because they're on the other side of my equation. And these two factors themselves have a common factor of n plus 1, so there's an n plus 1 in the denominator. And then that is multiplying this term contributed in L plus 1, whereas this term with the n plus 1 contributed a plus, remember because this is on the other side of my equation, plus n over 2. Now, in the numerator goes the terms that remained on this side of the equation. They both have pn as a common factor, so let me factor that out and write it down separately. And then the factors multiplying pn are these, and they go in my numerator. Combining these two factors, you'll notice alpha is a common term in these two pieces. So the alpha is multiplying now n and then an L plus 1. So I have n plus L plus 1. And finally, the last thing multiplying pn is this term minus 1. So at this point, we now have the recursion relation we can use to generate the series and to understand its properties.